Hello, we're the Drone Recovery System Testing Group. My name is Eric Lefevre, and my teammates for this project are
Thomas Ewell,
David Vanell.
Winnie Wawero.
and Nathan Williams.
The objective of this experiment is to analyze the effectiveness of different deployment methods of a parachute from a drone in uncontrolled freefall. Our key question is, does a spring-loaded or pressurized deployment method result in a faster release of a parachute for a drone in freefall? Drones are versatile pieces of technology that are becoming increasingly popular equipment in many different fields, but they almost all have one thing in common: they are expensive. Crashing a drone often leads to costly repairs or replacements, which can be detrimental to small businesses and individuals. Existing solutions to this problem focus on preventing a crash from occurring through means such as sensors and rotor guards, but not all crashes are preventable. The most common way to protect an object in freefall is through the use of a parachute. So for our experiment, we focused on the challenges that prevent a simple parachute design from being implemented. During our research, we discovered that the biggest hurdle was that while a drone is falling, it is often tumbling or flipping rapidly, which prevents a parachute from opening, as the cords would wrap around the drone and get tangled. To solve this problem, the parachute must be rapidly ejected so that it can open and slow the rotation, following conservation of angular momentum. Our test focused on the preliminary testing of this experiment to determine if either a spring-loaded system or a pressurized system could be an effective propulsion method. The results of our test would lead to further development of a product that could be installed on an actual drone and tested.
Here's a list of all the equipment used and their cost breakdown for this experiment. As shown by some of the images on the right, we used a tubeless tire valve, a CO2 tire inflator, 12 CO2 cartridges, an 1-inch diameter PVC pipe, two PVC end caps, a parachute, and a string. The total cost for this experiment was $44.33. This experiment posed minimal risks, yet precautions were still taken to mitigate any chance of harm. Initially, a secluded place away from high traffic areas was used. Furthermore, all participants wore safety glasses throughout the entirety of the experiment. Additionally, the PVC housing was regularly checked to ensure that no debris was present leading to unexpected projectiles. The test area had to be well ventilated, for this prevented potential CO2 poisoning with side effects such as headaches and dizziness.
the test begins by assembling the deployment housing using materials previously described. The 2-foot PVC pipe is cut into two 1-foot sections to be used for each test. A drill press is used to cut a hole in the PVC pipe for the quick release pull pin for the spring loaded test, and the PVC cap for the pressurized test. Once assembled, the housing is placed onto the floor and a tape measure is hung vertically directly above the housing. For the spring-loaded case, the springs are fully compressed and the quick-release pull pin is inserted. The parachute is then folded and packed into the housing as recommended by the National Association of Rocketry. A high-speed camera is set up so that the entire experiment is in view. The video starts and the parachute is deployed. Using the video, the maximum height of the parachute is determined as well as the exit velocity. Steps 5 through 8 are then repeated for the pressurized case.
Pictured on the left is a diagram of the proposed experimental setup with the key equipment labeled. Both pressure and spring-loaded systems are pictured, but only one is tested at a time. Now pictured on the right is an image from testing of the used experimental setup. The tape marks that you can see are at 6-inch intervals to allow for easier data collection and determination of the results. The video on the left shows one of our spring-loaded tests. And now the video on the right shows one of our pressure-based systems.
This current slide shows the overall results found in this experiment. In the case of the spring testing, 10 total deployments were acquired. For this method, we found the average height of deployments to be 4.075 feet with a standard deviation of 0.707 feet. The time required for the parachute to hit its apex was 0.468 seconds, and the average exit velocity was 16.28 feet per second with a standard deviation of 2.602 feet per second. When looking at the CO2-based deployment, 20 trials were taken. This was due to inconsistencies while trying to get multiple deployments per gas canister. The average launch distance for the CO2 trials was 5.795 feet with a standard deviation of 1.157 feet. The time required to reach a peak for the CO2 test was 0.546 seconds. Lastly, the mean exit velocity was 19.3 feet per second with a standard deviation of 3.24 feet per second. In comparison between these two, the spring-based deployment was less effective in both the height and velocity achieved. Despite this, it was found to be more consistent when regarding the comparison between the CO2 deployment. This, again, was due to the fact that the CO2 canister would run out of gas per trial, so we could only get 1 or 2 trials per canister.
Based on the testing and analysis performed, we determined that the CO2 deployment system had a higher average exit velocity when compared to the spring-loaded system. However, the spring-loaded system was more consistent in both the height launched and the exit velocity. As this was a preliminary test and for proof of concept, the team decided that both methods of deployment were viable, each with benefits and their own drawbacks. In this experiment, we found our main sources of error to be packing the parachute in technique and not being consistent between tests, as well as the spring system not being secured and that the tape marks used for measurement may not have been perfectly accurate. The next steps for this project would be reducing the overall size of the system to become better applicable for the frame and carrying capacity of a drone. Thank you.